Hi everyone. My name is Sasha Zelanovic, and I manage AI developer marketing and advocacy. I've been part of these office hours since day one, together with Michael Goin. Nice to see you again, Michael. I think if you are oh, can somebody mute? Hello? Okay, great. Sorry about that. So if you are regular at office hours, if you've been here, you probably know me and Michael. If you're new to office hours, welcome. We love having you. We meet bi-weekly, but it's been weekly, as I mentioned before, in January. And it's looking like a weekly in February too. So maybe we should change the top left of the slide to say weekly vLLM office hours, but we'll cross that bridge when we get there. So again, if you're new, we typically start with a vLLM project update from maintainer Michael that I mentioned, and we go into special topics. And today we're really excited about it. So Ali and Zevan, welcome from Cohere. And then Kyle and Brian, welcome from Red Hat AI. They'll be covering recent updates to the LLM compressor. There was a recent release that went out. So we'll cover that and probably more. And we'll also share a production case study that Cohere has been working on. So really excited to see how LLM compressor is being used in the wild. So Michael, if you can please go to. Yeah, LLM compressor update and a case study today for office hours on the 29th. So next Thursday, we'll be deep diving into the vLLM CPU offloading connector. Michael briefly talked about last office hours. All the office hours are recorded, so you can actually reference that from last week. And then we'll also be talking about the vLLM Triton backend on February 12th. More sessions are being discussed. We just haven't put them on the calendar yet. Once we do, we'll definitely let you guys know. Again, they're all recorded. They're on the YouTube playlist. You can always check them out. They're time-stamped. All of the recordings do come with slides. So if you just click the YouTube description, you'll be able to reference the slides as well. And Michael, what's going on in the vLLM space in the last week, I guess?
Yeah, thanks for kicking us off, Sash. We've had a lot going on in vLLM. So good to see 0.14 update. Which is really on time, as well as some exciting news. Sorry, what was that,
Is it my internet connection, guys? So, yeah, okay. So Michael, I think you're having some audio issues. Okay, thank you guys so much.
Give me 1 sec.
Yeah, maybe cut the camera. He is on the office. It looks like he's in the office, so this should not be an issue. But I can let me see. Oh, there he is. Sorry about that. He's quantized. Hi, Michael.
I love quantization, but maybe not on myself. Am I better now?
Much. Yes. Fully dense. Let's go.
Okay. Yeah. Let me just reset things up here. So everyone has access. Okay, that should be good. Yeah. Hey, everyone again. Thanks, Sasha, for kicking us off. And yes, if you couldn't hear me before, we did have a lot to update with vLLM since the past week. We had the 0.14 release. They went much more on time, as well as some big vLLM-Omni model releases, which we're excited to see pushing forward new model support there, as well as some big news for AMD users of vLLM. So let's get started.
Yeah, I can do this. Sorry, I'm laughing on the quantize. It's a great AI joke. So we are back on the road with vLLM meetups. We're looking, I think we have 12 to 15 already planned for Q1. You can see the list here. Munich is happening. Well, there's one in India happening on February 7th, but one that the registration is already built for is the Munich for February 24th. So if you have colleagues, friends, or communities in Germany that you're active with, we would love for you to forward the invite or come join us yourself. And then you can see we'll be pretty much all over the world, India, Japan, New Zealand, US, and New York City, Europe. Michael and I will actually be in both Warsaw and Vienna. I know there's some people from Vienna here already, so we would love for you to join us. We don't have registration pages for all of them. We're in the process of building them, so hopefully next office hours we'll have a better update, but you can get an idea of where we'll be on the road, and obviously we'd love for you to join us. Okay, I'm going to pass it over back to you, Michael.
Okay, thanks a lot, Sasha. And I am really excited for a lot of these meetups. Should be fun. But to introduce you to vLLM if you're not already familiar, it's the open source standard for inference and serving of large language models in production. It is that way because it's popular, easy to use, and most importantly, fast, supporting over 100 plus, maybe even 200 plus now different model architectures, and supports key models as they are released on day 0. We're able to do this because, of course, its popularity within the community, but due to a wide variety of support from academic institutions and major companies. You can see some of the 50 plus companies which have contributed to vLLM as over 2,000 different contributors. Thankfully, Cohere has contributed as well as us from Red Hat, it's in addition to the model support, it also supports a wide variety of hardware accelerators. So getting great performance not just on NVIDIA GPUs, but AMD, Intel Gaudi, Google TPU, and many, many more, which you can see from the list here, due to our flexible hardware plugin system. Then we can run those models across more than just one device, but running a single model like DeepSeek R1 across 8 devices on a single node with tensor parallelism or expert parallelism, and then expanding that to run across multiple nodes. So now running a model on a cluster of GPUs with fast interconnect like ROCm, with wide expert parallelism and disaggregating prefill and decode, all sorts of features and optimizations that are used by model providers at scale, which is why vLLM is the base for so many large-scale deployments, with people forking and making their changes as they need. And of course, vLLM, while it's an inference engine and ecosystem itself, it's also full of many other projects, of which, of course, LLM Compressor is one of them, as well as Speculators, which was talked about last office hours, and many of the others, at the bottom of the list here. So, we're very excited that vLLM has grown into such a large ecosystem and community for ultimately making inference more efficient and easier to scale and achieve. So as I mentioned before, there were some exciting model releases over the last week. Particularly on the multimodal side, we've had Flux 0.2 Klein from Black Forest Labs and the Qwen 3 text-to-speech models, both of which are really impressive in benchmarks and usage in their own right. Obviously, image generation and speech generation. But both of these work on day 0 in vLLM-Omni, which is a really good sign that we're on the right path for supporting models and supporting workflows and interfaces that people want to use these models, and the model foundation labs themselves are happy to help us support. So really excited about these, and they're really cool models. I especially the Flux Klein model is a really impressive for how small of a model it is, and you can probably run it on your own local GPU at home. So without further ado, we'll get into the vLLM release here. I have some highlights, things that you should really be on the lookout for. So async scheduling is now enabled by default. You no longer need to opt into async scheduling with the flag. This is because it works now with a lot more features. Of course, there's still some features it doesn't support, which will automatically turn off by default. So you shouldn't worry about that. However, if you do run into any issues, first, please let us know. And second, you can still add --no async scheduling in order to disable it and make sure that that's a async scheduling related issue. We still have some more features we're working on supporting, like pipeline parallelism and more speculative decoding methods than MTP or Eagle. But things should be pretty good, and you should be able to see the performance benefit from async scheduling across a lot of scenarios now. Another performance benefit that's coming that has come in this release for large-scale serving is the gRPC server endpoint. So for a long time, vLLM has had a fast API server endpoint. This is the VLM serve you're used to. But now we have an alternative to the REST API using gRPC for deployments that want to build their own lower overhead infrastructure and sort of build their own model gateways or endpoints on top of VLM's base server, still handling a lot of things. So yeah, this should be hopefully interesting to some of the power users that have already probably forked VLM and built their own server entry points. But now we're standardizing this with a gRPC protocol and pushing performance there as we scale to larger and larger deployments. Next is a feature that actually two features that I worked on myself that I'm going to plug, but I think are pretty useful. So for the longest time, if you use VLM on a GPU with not much memory, you know that VLM uses the full context length of the model by default. And sometimes this can run out of memory if you can't fit the full context length. So now we started to introduce this max model length auto flag, which will now automatically shorten the context length if your GPU can't fit that much. This is still an opt-in feature, but it's something that we're considering to turn on by default, just to give a better user experience, of course, with a loud warning that you're not using the full context length of the model. Yeah, please give it a try. If you've been setting the max model length to shorter values manually for a while, please give auto a try and let us know if you run into any issues or it's not working for you. Second, we have this model inspection view, which you can activate through an environment variable, VLM log model inspection, which will print during startup, right before model weights are loaded, actually, or by just printing the final LLM object in Python. And this will now give you a PyTorch module list style, or if you use transformers and you print a transformers model, it'll give you a now module by module view of your VLM model graph. And of course, it's going to show obvious things like your linear layers and your embeddings and RMS norm, but it should have some extra information there if you're running quantized layers or attention backends, letting you know which attention backend or kernel is being used. And similarly, if your QKV modules are quantized to FP8 and maybe your MOE modules are quantized to FP4, you'll be able to see this quantization within this module graph. And we're looking forward to expanding this functionality more so that we can offer hopefully more abbreviated summaries of what kernels are we using for what operations in your model. So it becomes more clear if you're using what you expect, using Flash Attention 3 when you expect, and so on and so forth. So again, please give this a try and let us know if you run into bugs or you'd like to see other features added, and feel free to contribute to it yourself. And again, going back to Model Runner v2, which you've had several updates over the past few releases, we're making good progress there. It's still experimental and something we're building on the side, but we are getting close to feeling we can enable it for a variety of simple scenarios. Now working more carefully on CUDA graph and spec decoding support. So now on the more verbose list of features, we've had a lot of model releases that have been from the past couple of weeks, since this is a bi-weekly release, including the Liquid's second iteration model that focuses on vision language inference, also Mimo v2 Flash, a key agentic model, and an ASR model from GLM, the ZAI group, and several other models. We've also been pushing LoRa support in many more models, generalizing that, particularly for multimodal and encoding models, as this is also used as a core base for vLLM-Omni, building towards there as well. As I mentioned, a lot of work on supporting things for async scheduling so we can turn it on by default, as well as generalizing the Triton attention backend to support more of our model architectures and usage, so it can be a good general backend for most cases and hardware platforms. Next, we have had a lot of hardware and performance improvements, especially for Hopper and Blackwell GPUs, as well as Blackwell preparing for Blackwell Ultra with SM103. So we've added general support and testing for that. GB and B300. So most kernels that run on Blackwell should now also run on Blackwell Ultra. We're still working on tuning performance there, as we will need new MVFP4 kernels to take full advantage of that hardware. But as I mentioned, we have been working on a variety of general optimizations for FP8 and NVFP4, Cutlass MOE, where we've been squashing a lot of overheads and fusing several kernels together for that pathway, improving the default throughput performance and a bit of latency improvements as well. Yeah, many other updates here. The Model Bash group has been working very diligently on squashing performance, especially for large MOEs. So really happy with the progress there. With respect to large scale serving, we've been focusing heavily on generalizing many of the initial features we made, such as dual batch overlap, now generalizing to N or X batch overlap, so you can have more than just 2 micro batches in your in order to overlap your dispatch and combine with compute for large scale DeepSeek inference. Many features related to robustness for either YDP or DISAG PD, with Nixel and EPLB as the main focus there, both in performance actually and robustness. With respect to quantization, we've had a lot of updates to the Marlin kernel. Most notably, the minimum supported CUDA version or CUDA compute capability used to be SM80, so Ampere GPUs and above, but now we've added support for Turing and above. As we will probably deprecate Volta support soon, since PyTorch 2.10 unfortunately deprecated it, and so we'll probably follow. We'll likely be able to use Marlin for all of the weight-only quantization, kernel, all the weight-only quantized models in the future, at least as the baseline implementation. Yeah, that's all I'll cover there. And then on the API and front end, I've mentioned already a lot of these front end features in the highlights. But I will note that we have started working on MFU metrics. Still just a basic utilization metric that's focused on simplicity rather than accuracy. But if you're interested in looking for compute utilization, profiling and logging for vLLM, there's a good base there to start. Yeah, and then just various other API updates, bug fixes, and things that we found during the release process, and from issues reported since then. Yeah, we have, and with respect to breaking changes, AC scheduling is on by default. This should be okay. We have a lot of testing around this, but please let us know if you run into issues. We very much want this to be on by default in as many cases as possible. Also, a small note, with the default wheel of vLLM now being compiled to CUDA 12.9 instead of CUDA 12.8. This is in order to match what PyTorch is doing by default now. Shouldn't be any issue for users running CUDA 12.8. It should be backwards compatible, but an FYI there. We have started removing quantization schemes as listed in the RFC, which you can find by clicking through some of those PRs. We do this based on usage, and we have dozens of quantization backends in vLLM, so we're just trying to clean those up and focus on the ones that are heavily used and we want to maintain going forward. And then the last thing on this release, the AMD team, in hand in hand with the community and us core committers, have done a great job bringing upstream vLLM support for ROCm, now hosting official upstream wheels on the vLLM Wheels repository, as well as the vLLM Docker Hub repository. So if you go to the vLLM.ai quick start, you can now look at the ROCm selections and get very simple pip install and Docker run commands to run with the official upstream version. And as well, we now have AMD CI, close to being enabled on every commit in upstream vLLM. So very much thanks to the AMD team for pushing the quality of CI and release in upstream vLLM to a much better state, or a better state than it's ever been. So that's all I want to cover. Thanks a lot for letting me take the time. Now I'll pass it off to Red Hat and Cohere folks to go over LLM Compressor.
Cool. Thanks, Michael. Yeah, really quick here. I'm excited to talk about LLM Compressor and kind of share our most recent updates with the tool, as well as hand off later to Zewen and Ali to talk about our collaboration with Cohere. Cool. So really quickly running through the agenda today, we're going to talk a little bit about LLM Compressor, where it's used and why you should be using it. We're going to talk about all of the updates that come with our latest release of the LLM Compressor 0.9. So things like attention quantization, additions of modifiers like the AutoRound modifier, and then also our improvements to performance in AWQ, and then also moving forward. And then finally, we'll hand off to Ali and Zewen to talk about our use case with Cohere. Cool. So for those who are unaware, LLM Compressor is a repo maintained primarily by Red Hat AI, but under the vLLM organization, which allows you to take base models, compress them into arbitrary quantizations, and then serve them directly within vLLM. It kind of sits in the middle in the ecosystem between full precision models and then running those quantized models within vLLM. So jumping here. So in our latest release of LLM Compressor, we've mostly focused on kind of refactoring a lot of our kind of older code, specifically aiming at refactors which allow us to do more generalized quantizations. So different kinds of quantizations like MXFP4, things like quantizations on attention and KV cache, arbitrary quantization there. As well as kind of at the end of this quarter and as well as like moving forward into our next release, focusing heavily on performance optimization of LLM Compressor, being able to compress models really, really fast with as few GPUs and resources as necessary. So we'll talk about our first kind of refactor here. Our big thing that we were focused on with this latest release was with attention and KV cache quantization. So you may be aware of KV cache quantization in vLLM. KV cache quantization allows you to take your KV cache and quantize those cached KV values, thereby like reducing the amount of GPU memory that's required in order to kind of serve your models, especially for model use cases where you have a very large context. KV cache quantization is especially applicable. However, KV cache quantization in vLLM is a little bit under-supported in the sense that it only supports FP8 quantization, right? Whereas we all know that there are many other kinds of quantizations that we would want to support. And not only that, not only quantization of the KV cache, but also of attention. So here we kind of have an example of kind of what a standard attention mechanism looks like within an LLM. The kind of like half-hashed blocks kind of represent where KV cache comes into play, right? So taking kind of the outputs of like the K-proj after the positional embedding is applied and the output of the V-proj and quantizing those values, right? Our previous implementation of this within LLM Compressor primarily focused on just FP8 quantization, and specifically just FP8 on a per channel basis. On a per token basis, per tensor basis. But we found that, this is a great starting point for sure. But we kind of found that our previous architecture and implementation of this was really, really focused on just that one use case. So in LLM Compressor v0.9, you can apply KV cache and attention quantization in arbitrary quantization schemes. So things like FP8, not but also int8, FP4, and int4 as well. Not only that, you can apply these within different kinds of strategies. So things like per channel, or things like even per attention head are all supported within LLM Compressor. As of currently right now, all of these features are purely experimental. So you're able to quantize models using these like kind of arbitrary quantizations. And you're able to run them within like the Hugging Face transformers, using the Hugging Face transformers models. But our hope here is that by kind of allowing these arbitrary quantizations, folks will be able to run experiments and kind of experiment with where does like accuracy loss come into play, how much accuracy loss you really see for all of these different kinds of quantizations. And then hopefully this can help enable users to not only experiment with quantization, but also motivate the implementation of these quantizations within vLLM natively. Yeah, so really exciting stuff there. Moving on, so another kind of like somewhat experimental feature we've been implementing is called the model-free pre-TQ pathway. So normally within LLM Compressor, you might load a model within a Hugging Face definition, and then kind of run through that model, calibrating it or quantizing the weights, and then finally saving your model within the Hugging Face kind of format, right? For serving with vLLM. This is a great pathway for most models that are well supported within like the Hugging Face Transformers library. However, there are lots of models that aren't well supported within this library. Among those are things like Mistral models, just kind of lacking support there, which has made it very difficult to work with like Mistral models within LLM Compressor. Not only that, but also kind of models where you know, it might be released like within a day or so, right? So being able to support models being quantized on a 0-day basis basically requires that we have some way of kind of applying quantization without relying on a very formal Hugging Face model definition. So that's where the model-free PTQ pathway provided by LLM Compressor kind of comes in. So all you have to do is point to a folder containing safe tensors files, and this function will basically take those weights and quantize them and then save them back, right? Without involving any model definitions at all. Obviously, this is a very like easy to use kind of pathway. And it can also be faster in the sense that it provides multi-threading support. However, there are also limitations to this kind of pathway, right? You can only do it with data-free schemes, so schemes that don't require actual calibration of the activations. But we found this to be a really great feature and has allowed us to support quantization of the Mistral Large 3 models on a 0-day basis, which we released with them. So yeah, very exciting stuff there. Finally, for me, I want to talk a little bit about our latest contribution to LLM Compressor from Intel called the AutoRound modifier. So LLM Compressor is kind of has a collection of algorithm implementations. These algorithms are implemented with the aim of quantizing models while providing the highest accuracy recovery that we can, right? So things like GPTQ you might be familiar with, or AWQ. In addition to this, we've also had a contribution from Intel of the AutoRound model that implements the AutoRound algorithm. AutoRound is an algorithm which is designed to provide very high accuracy recovery for weight quantization. Specifically, it does this via kind of like small gradient descent update steps. So you can see here that in this example, we have like a weight, and all the AutoRound modifier does is it adds 3 new trainable parameters to these weights. So at the top, you can see that there is an extra V parameter that is added to the weight. This V parameter is bounded or constrained in its optimization, so it can only go to -0.5 or +0.5. This V parameter is learned to control where kind of the boundaries of quantization occur, so where that bucketing occurs, right? In addition to learning that V parameter, we also have 2 other parameters, the alpha and beta parameter. Alpha and beta control kind of the clipping of of the max and min values during quantization. Clipping is often something that is like a kind of hand-tuned parameter. Either we set it to 0 or we set it to something very small like 0.1. AutoRound kind of allows you to do mini-batched learning of these clipping parameters. And the authors have basically found by just optimizing these 3 parameters, basically parameters on the quantization itself, they're able to achieve really good accuracy recovery, really strong accuracy recovery for low bit quantization, rivaling GPTQ. Yeah, so kind of moving forward, here are some kind of like code snippets of like how you might use the AutoRound modifier. You know, if it fits directly into the LLM compressor framework, where you simply add the modifier to your recipe and then apply your recipe to the model. And you can see here that we validated really strong recovery results using the AutoRound modifier within LLM Compressor. So when you're applying quantization like W4, A16, or other kinds of quantizations, this is another kind of tool in your toolkit to be able to kind of play with and experiment with algorithms that maximize your accuracy recovery during quantization. Cool. Yep, just kind of calling out here that you know, AutoRound supports not only W4A16, but lots of other schemes. You know, kind of tying into our general theme of this release, which is to kind of generalize all the quantization schemes that you can apply within LLM Compressor, and having those being fully composable with all of our different modifiers. Cool, exciting stuff. I'm going to hand off to Brian to talk about AWQ enhancements, and then also kind of roadmap of LLM Compressor and performance moving forward.
Thanks, Kyle. Yeah, so just wanted to share with you guys quick. We spent a lot of time in Q4 looking at our AWQ implementation and different ways to enhance it, both in terms of the runtime and just the flexibility to run with other compression schemes. So this is actually one of the first projects I did in Q2, one of my first projects here, where we pulled, basically kind of pulled as much as we could from the auto AWQ port just verbatim so that we could get, we could just kind of copy what was already available. We've moved from that to pulling in more of our primitives and our abstractions inside LLM Compressor and compressed tensors. And just by way of this, rather than having like hard-coded schemes like W4A16 or the ASIM version of that, which are what AWQ was originally intended for, we can move beyond that now to allow for any of the schemes that are available in compressed tensors just by using the primitives. So, you know, it gives us a much broader flexibility here to try out, especially NVFP4 and NVFP4 A16 variants. There's AWQ can be a kind of an expensive algorithm and involves a grid search over a pretty broad search space. The default is 20 grid points. We found just through running these that some of the grid search defaults, the way it was defined, were actually not as good as they could be. So we had enhanced that with some better defaults. We also have better MOE support. It involves, the algorithm itself involves finding mappings where you have some linear feed into another linear layer, and then you can scale those weights accordingly. It involves, you know, manual inspection of the model at runtime, and so we've made that a little bit more robust. And then lastly, for runtime improvements, I will share more on that the next slide. We were spending some time just figuring out what is the bottleneck here and maybe how can we improve that. And happy to report that I think we found some really good results here. And then also moving forward, this is really a request by the research team. We want to be able to kind of stack these algorithms together. For example, running AWQ on the same layers in one pass of the pipeline, and then running another compression algorithm like GPTQ before quantizing. So just providing a whole bunch of flexibility here so that we can really expand our benchmarks and what we're viewing. And so I mentioned this runtime improvement. That brings me to what we're calling batch calibration support. So AWQ, just like GPTQ or the NVFP4 modifier, will use what we call our sequential pipeline, where components of the model will be loaded on, and you only inspect that one decoder layer or that one MLP layer at a time, and then you can offload it and bring another one on. In doing so, we were using just a single, our forward passes would be a single batch, or a batch size of 1. And we didn't enable this for concerns about memory usage and other things, but we found that actually adding these as fields to our one-shot out, our entry point, which is the main entry point for all of these. If we're using AWQ in our recipe, all we need to do is add another field for batch size and how we want to collate the data, either truncation or padding. And I found just running these just out of the box examples, not trying to fine tune anything on Qwen 330B. The speed up can be marginal for GPTQ. 50. I mean, it's still nothing to. It's still a good enough savings to be of merit to like want to try this out. GPTQ doesn't rely on this kind of grid search and forward passes through the model like AWQ does. So a lot of our bottleneck was because of that. So by doing this, by switching from batch size 1 to 32, we can reduce the runtime by 60%. So over half the runtime can be reduced this way. So a big savings. We're hoping to try this out more, especially as we do more general benchmarking with, say, like AWQ or plus GPTQ or AWQ with NVFP4. So yeah, wanted to highlight that as kind of a win we didn't know what we would find in Q4, like in terms of improving this, but it turns out after a few null results, like things that we thought would help didn't end up helping, that this was actually a very key for that. And then, so lastly, that kind of brings us to what we hope to do in Q1 2026, VO.10 and beyond. I've linked an issue down below. This is an RFC that Deepika on our team has created, including a series of RFCs for each of the things you see here, as well as our overall goals moving forward. So one thing, I think primarily the biggest thing right here, distributed quantization support. Essentially, when we run our sequential pipeline, everything runs on a single GPU. We want to be able to enhance that by allowing data parallel pipeline, and then also parallelizing the modifiers underneath that. So AWQ, when you're doing your grid search, or GPTQ, when you need to compress the module. If you have multiple modules in that subgraph, you can do that all at once. So there's both a data parallel scheme that can improve, as well as a per modifier enhancement to speed that up. So a big focus for us moving forward is that. We also, we've enabled MXFP4 support kind of as an experimental feature. We want to be able to go deeper with that, including MXFP4 activation support, not just with the weights. Transformers v5 is also coming up, so there's some considerations for compatibility with that. And as Kyle mentioned, with some of our transforms related work, there's growing research. Dan Alister's group that we collaborate very closely with has worked on NVFP4 with micro rotations to improve or reduce the quantization loss according to that can come up with that. So we hope to both add this as a feature and then do a whole bunch of benchmarking across all these different modifiers, as we have just a ton of these now. We have AutoRound is being introduced. We can stack these. There's a whole lot of tools in our tool belt, and I think we need, especially for the community, how to explain what to use and when to use it. And that also kind of brings me to this QR code. This is the first time we've tried this, a little pet project of mine. We have a lot of these algorithms. We have users report issues. But I think like having a little bit more information, what people are struggling with, what are pain points, what do you like, what are you really focused on when it comes to compressing a model. Please take our 1-minute survey. It's linked in the slides as well, or in this QR code, or any comments on the RFCs that are associated with this issue, 2262. We'll be sure to take a look at. We don't collect any statistics as you run LLM Compressor, so a lot of this we can kind of fly blind a little bit. So I think it can be really helpful as we determine where we should invest our time for development. So that's all I have. I want to pass to Ali and Zeman, who've been super kind to share with how they are using LLM Compressor. They've been really great communicators and collaborators the past year or so. So really excited for this. I'll share it to you guys.
Okay. Thank you for the introduction. Hi, everyone. This is Zoen from Cohere. And today, Ali and I am going to talk about how we use LLM Compressor in production. Many of clients deploy models in private on-prem environments, and their GPU resources could be very limited. At the same time, many of our production models use MOE architecture. So this significantly increased the memory footprint during inference. And without 4-bit weight quantization, these models could simply be too large and too expensive to deploy in practice. So it's pretty much a hard requirement for us to deliver high-quality W4A16 and W4A4A8 models. And we chose LLM Compressor for our daily quantization work because it provides us with many out-of-the-box quantization algorithms that are easy to adapt to our internal model architectures. And another feature we really like about it is the non-uniform quantization. It helps us to study the layer-wise sensitivity of our model and combine different algorithms and precisions for getting the best performing quantized model. Also, on top of that, its modular design and type integration with vLLM allows us to iterate much faster on our experiments. And next, I'm going to talk about the background story of our recent experience. At Cohere, we developed an enterprise AI platform called North. It is used for building secure, production-grade AI agents that automate business workflows. And our models are trained to operate in this environment with very strong tool use and agentic capabilities. When we quantize these models, it's not sufficient to just preserve the academic benchmark accuracy. Our model has to continue to perform well inside the North environment. And recently, we used AWQ from LLM Compressor for the 4-bit weight quantization. However, when we calibrate the AWQ using the standard setup, which is basically using the UltraSep dataset with a maximum 2K sequence length for calibration, we observed the noticeable performance drop in North. And in order to understand what's going on, we analyzed the failure cases in more detail. We found that most of the issues happen on the agentic tasks that require long context, often far beyond 20K tokens. So we think it might be a good idea to use some internal agentic traces for calibration. These traces contain very long instruction chain with multi-step reasoning and tool use. And the sequence length ranges from 1K up to 64K. But unfortunately, even with this new data sets, the quantized model quality was still not good enough. So we take a closer look at our calibration data. We noticed that a large portion of the tokens came from the system prompts and tool descriptions. These parts are very long and highly repetitive. They're also not representative of what the model actually generates during the inference. We know that AWQ relies on the mean activation magnitude to set the search direction in optimization. And because these repetitive activations dominate the statistics, they skew the calibration process and lead to a suboptimal search direction, which in the end hurts the model quality. And in order to fix this, we added the support for token masking to AWQ in LLM Compressor. This allows us to exclude repetitive tokens, such as the system prompts and tool descriptions, from the calibration statistics. And by leveraging the existing state system in LLM Compressor, we only need minimal changes to the core AWQ logic. The same design can also be reused by other quantization algorithms. to support the token masking. And with this token masking enabled, we were able to produce production-ready 4-bit models that meet our internal quality standards. The LLM compressor library gives us the flexibility to quickly fix real production issues and turn these fixes into reusable improvement for other algorithms. We also believe that this feature will be useful for many people, and which is currently lacking in other open source quantization library. This is because nowadays the system prompts are getting longer and longer. We know that, for example, the Cloud Code uses the system prompts that are very long. I think it's beyond 20K tokens. And I'll leave the next slide to Ali.
Thank you, Zuban. Hi, everyone. This is Ali from Cohere, and I'm going to cover the next slides. So the initial AWQ implementation only supported int4 weight-only quantization, but more and more customers are using Blackwell GPUs, which natively supports NVFP4 quantization. And this motivated us to add the support for NVFP4 weight-only quantization to the AWQ implementation in LLM Compressor. And thanks to the modular design of LLM Compressor, we were able to add this feature quickly and smoothly. And we were able to get really good results with AWQ when we use it for NVFP4 weight-only quantization. So the below table shows the quality results of one of our models. When we applied AWQ as well as the token masking feature that was previously mentioned to quantize it to NVFP4 weight-only quantized version. We used both round to nearest and AWQ, and as the results show, with AWQ, we were able to recover most of the quality drop compared to BF16. So the aggregated logic relative drop means the drop compared to BF16 on a benchmark that is made by some widely used reasoning tasks like GPQA and AMI. In addition, we used LLM Compressor for W4A8 quantization for Command A reasoning. So Command A reasoning is a Cohere model, and W4A8 means applying per group int4 weight quantization as well as per token FP8 activation quantization. So the motivation here is that W4A8 achieves significant speed up compared to W4A16, especially in computationally bounded scenarios. For example, the right two plots show the TTFT and TPOT of Command A reasoning quantized to W4A16 and W4A8. And as the results show, by doing W4A8 quantization, we are able to get significant speed up compared to W4A16. For example, around 40% in TTFT and about 20 to 30% improvement on TPOT. Serving W4A8 models, I mean, both dense and MOE models have been supported in vLLM from our team. And we applied AWQ from LLM Compressor as well as the token masking feature that was previously mentioned to achieve accurate and high quality W4A8 quantization for Command A reasoning. And we observed similar gains when we applied this for MOE models as well in terms of quality and performance. So these are some of the examples of using LLM Compressor in our pipeline, and we are looking for future collaborations with the LLM Compressor team. Thank you for your attention.
Thanks, guys. I just want to call out like this idea of like the token masking was something that I think we were completely unaware of the benefits of doing that. And one of the highlights of this collaboration is seeing, beyond the LM evals we do, when there's a long context window or a large prompt, how much that matters when doing these. So a really good insight. I think, oh, go ahead, Michael.
Yeah, definitely. Thanks a lot for sharing. Yeah, do any folks have questions? Obviously, there's been a bit of back and forth in the chat, but if people want to come off mute or ask things live or more in the chat. It was definitely a great overview over what's new in LLM Compressor. Yeah, go ahead, Shrikant.
Yeah, hi, Michael. So I'm just wondering if there is any blog article that showcases the difference in terms of, accuracy as well as throughput when it comes to model post and pre-employment of LLM compressor techniques, because we are seeing the new compressor libraries coming from other players in the market. So we just want to put it through the numbers, and then we have to be compared by the other libraries. Yeah.
Yeah, so it sounds like you're asking for a few different things. So like showing how accuracy works for a variety of quantization methods, but also how the performance changes for those methods. And then also comparing implementations between different compression libraries.
Correct.
Is that right?
Yeah.
Yeah. I think like, yeah, maybe like a good thing to start is that I mean, to be frank, like most compression libraries, at least that are implementing the same algorithms, should be like pretty similar in terms of like the accuracy results. The biggest thing that might change is like the data set or calibration you choose, which is why, we recommend probably, being intentional about what calibration set you're using. And then, in terms of like the final performance of like a given quantization type in vLLM, from vLLM's perspective, it's not really going to distinguish if a quantized format was, or if a quantized checkpoint was made from one, compression framework to the next, unless it's like saving in like a wildly different format or different shape of scales, doing like group scales instead of channel-wise scales. Generally within vLLM, we're using the same kernel to run a model that's at a certain precision. Yeah, you can kind of like separate those things at those angles. And then there's like, specifically for like, accuracy across different precision types, there's a lot of blogs and papers on that. We had like a paper, I think last year, like the Give Me BF16 or Death paper that goes over like a lot of this for FP8, INT8, INT4 methods, sort of showing some of those things that Brian, I think, already touched on, of like where we go beyond the basic open, LM eval benchmarks and go into like long context evals and more challenging evals. Yeah, which like you can see a lot of those in the Hugging Face model cards of the day now. Yeah, it's still something that depends on your specific use case, but there's certainly a lot of reading available out there.
Yeah, I'm also going to add my 2 cents here. So, I mean, as Michael kind of mentioned, like LLM Compressor is not the only like quantization library that supports model optimization. However, like there are a lot of things that make LLM Compressor especially useful as a library. I think like, having a comprehensive set of algorithm implementations, and then also having those algorithm implementations fully backed by the Red Hat AI team, in terms of like having the right kind of parameterizations of those algorithms, and then also like being able to provide kind of pre-quantized models that you can run within vLLM is also like another benefit. So being able to like run these algorithms with like high confidence that you're going to get the best accuracy recovery that you can, and the quantization process itself is going to be as easy to use as possible from like a performance perspective, from like a memory perspective, to like maximize how fast you can iterate. Yeah, not to mention that we're also adding new algorithms on a regular basis, things like transforms, which we talked briefly about, and then also things like attention quantization too.
Okay, thanks.
Yeah, I agree.
Plus,
Probably
I
the
think-
strongest point is finding a good community. Yeah, where you can quickly iterate.
Yeah. Plus, I think so with MOEs, like you have to figure out the correct way to do router compression versus the other weights and the expert compression. So that you're if you use FP4 or NVF4 with the routers inside the MOE, so that might not give you the benefit like as much as like using FP16 inside that particular router and then FP8 inside that particular exports. So like you have to kind of go that way too, to make your MOEs smaller with respect to both the latency as well as the other metrics that we have discussed about.
Yeah, totally. That's kind of like another piece of this puzzle too, is that quantization in itself actually requires, as you mentioned, kind of like special configuration sometimes. Like with MOEs, you have like that router layer, and that router layer, as you mentioned, it's like especially sensitive to quantization, right? So kind of having that kind of consideration is also something that LLM Compressor provides in our examples, and then also like general community support. If you quantize a model with LLM Compressor and you find that like the accuracy recovery isn't as much as you want, or it's not running as fast as you want, all those things we're able to provide support for, especially because, as you mentioned, quantization, it can take, especially with like routers, can require some configuration there. Thanks for the addition.
Yeah, I think this kind of idea of non-uniform support is something we want to push on even further and come up with tooling to kind of do it in an automated way rather than having the user manually inspect reconstruction losses for each layer, that sort of thing. Something we've talked about for this year.
Yeah, go for it, Thomas.
Yeah, this question will be a bit broad because, excuse me, I'm new to LLM inference. What I'm wondering is, like for a large production model, quote unquote, how much are you able to see like memory reduction before you see major degradation of quality in the model itself? Like, yeah, how much are you able to reduce your memory footprint with this on average, across like multiple use cases that you see with customers?
Yeah, I think that's a great question. I think the general trend with larger models is that they actually are easier to quantize than smaller models. So the larger you go, like the more likely that your quantization is going to have the highest accuracy recovery you can. But if you apply the right algorithms, which are available on LLM Compressor and other repos as well, you should be seeing like close to lossless, definitely lossless for FP8 for sure. In kind of like int4 cases and like FP4 cases, you might see some like slight losses. But we've been working with like researchers at IST, as well as kind of reading like the latest papers in order to like implement algorithms to cut that margin as small as you can, right? So to answer your question directly, things like FP8, basically lossless, and that's going to cut your memory footprint by half, right? Going from bfloat 16 to FP8. For lower quantizations like int4 or FP4, you may see some losses in some cases if you're not like applying the right algorithms, or if your model is particularly hard, or you're like quantizing the wrong layers, that may also be an effect. But lower bit quantizations like int4 and FP4, you're going to see a 4x reduction on your memory size. Does that kind of answer your question?
Yeah, totally. Thank you.
Awesome. Yeah, and all of those, if you go on like the Red Hat AI Hugging Face organization, you'll be able to see like a whole collection of quantized models that have been compressed with LLM Compressor, and each of those model stubs shows the accuracy recovery that you can expect.
I just pasted one in the chat, Thomas, if you want to take a look there. It's like, you can see like, it will go through each of the evals, and it's really nice. They show as much as they can how to reproduce 98% recovery going to W4A16 on Qwen 3 next.
Cool. I think we're pretty close to time. Yeah.
Yeah, thanks a lot for the insightful questions. Yeah, I mean, thanks again to Kyle, Brian, Alize Wen for the update on LLM Compressor and yeah, the usage of it. Definitely cool to see. Thanks for everyone for coming to another week of office hours. We have another one next week. Do we have another one the week after that, Sasha?
I think we might take a break and then the following week.
Okay, we'll go back to regularly scheduled programming after January. But yeah, make sure to come next week for the CPU offloading, KV offloading support, as we might be enabling it by default, and yeah, have more performance things to share there. So thanks everyone for coming. Thanks to our speakers, and hope you have a good week. Take care, everyone.